Hi, my name is Subodh Iyengar, and I work on the security infrastructure team at Facebook. So what we do is I work majorly on the Facebook for Android application, and I write abstractions to make coding more secure and mobile. So today I'm going to talk about some of the abstractions we've actually engineered in mobile development to make our code secure. So run through a quick agenda. So I'm going to give a quick overview of the challenges of organizational challenges of security scale in mobile development, and then talk a bit about the threat models we're concerned about in mobile platforms and some of the abstractions we've developed to address these threats. And also a bit about how we store data and manage user data securely on Android devices. So I work majorly on Android, so this is going to be a little focused, a little bent towards more about Android, but then I'll touch on iOS whenever I get the chance, whenever it makes sense to touch on it. So if you've attended one of our at-scale conferences before, for example, Mobile at Scale, you've seen such numbers, large numbers being thrown around casually, hundreds of engineers, 100,000 files, a large number of commits. But one number you haven't seen before, which I'm going to show you for the first time, is this. So there's there's 3 or so of us working on it. Everybody contributes to security, but majorly 3 people are focused on mobile application security at Facebook. So the challenge of scale is how do you prevent, or how do you make sure all the code that's being committed every day doesn't introduce new security holes in the application? That's a big challenge of scale. So security can devolve into this whack-a-mole situation where you whack one bug out and then another one pops out, which is sort of similar, right? You've seen that before. So that is simply not a scalable solution. So what we've tried to do in this case is the one thing that's helped us scale is creating these abstractions which will help us whack a million moles with one hammer. So the hammer being the abstraction. So then, and we try to make it such that we engineer abstractions which are secure by default. So they prevent not only bugs that are currently in place, but also bugs that would happen in the future of a certain class. So and another thing is we make tools to enforce the use of such abstractions and to detect bugs manually as well. So I'll talk about some of the abstractions in the subsequent slides. There we go. Another way we scale is that we actually immerse ourselves as security people, software engineers interested in security. We immerse ourselves deeply in the teams that we actually work with, essentially. So what we do is we work actively on product code. So we're actually software engineers first and security people second. And this gives us a better understanding of the problems of developers, product developers, so that we can engineer abstractions so that they can withstand the test of time, and hopefully the universe will be better after that. So some of the threat models that we're concerned about in mobile development are, I'll classify them into 2 categories. One is malicious applications and network attackers. So in malicious applications, users can download apps from untrusted sources. In Android specifically, you can download, because of the openness of the platform, you can download apps from any place on the internet. So, and they can do various things. So we think now it's not a big problem, but we think in the future, the mobile malware will match desktop malware. So we want to be prepared for the situation where to safeguard Facebook data, safeguard the users' data, Facebook data against malware applications, malicious applications. So another threat model that we care about deeply is network attackers. So basically, this is the man-in-the-middle threat model. So we want to prevent people, script kiddies who sit in cyber cafes and sniff on Facebook traffic, to governments who actually try to spy on their citizens through Facebook. So this is especially important for apps because unlike browsers, unlike web applications, because you have the buffer of the browser to implement all the SSL security for you, inside the mobile app, you have to implement all your SSL yourself. You have to manage connection pools yourself, HTTP yourself. So this gives you a lot of power, but with great power, there's more chances to screw up. So we want to prevent that from screwing up. So one of the classes of bugs that we which could cause data leak in other applications. I'm going to go through a list of classes of bugs which could cause data leakage to happen. So one of the classes of bugs takes this format essentially. So in this case, for people not familiar with Android, this creates an intent which is like a data packet, you could say. And then it actually sets some sensitive data in the intent, like some private data, could be secret data, and then actually like calls out, does a start activity to another component in the application. So start activity is like an IPC call in Android. So the intended behavior of this was to call another component inside the application. But because of the openness of Android, like other applications, including malicious applications, can also register for this schema and hence can hijack this sensitive data. So you can imagine like this mole exists in one form, but you can imagine like moles existing, such like bugs existing in different formats completely, like, oh, a little like change there and different permutations of this same bug. So we decided to like whack all the moles at once. So we created this abstraction called Secure Context Helper. Yeah, the weird name is because it's Java, but anyway. So then, Secure Context Helper has two methods, basically start activity and start external activity. So the rule is simple. Like instead of using start activity from activity class, you use start activity from the Secure Context Helper class. So why is this different from like using start activity essentially? So because this actually like by default, start activity in Secure Context Helper enforces security policies such that only the current application can get it. So what it does, it actually, like if you pass in an implicit intent, which is sort of like the intent that I showed you in the previous slide, it will dynamically resolve the intent and figure out like which component would be resolved to. And then what it'll do is like it will verify the signature of the component that is on the other side, and only dispatch, like once it matches, only then dispatch it to that component. So this, like, we retrofitted our own like security mechanism on top of the Android security mechanism to enable like we use this for like multi-app communication. Like we use this to communicate within our internal app all over the place. Another, so if you like, sometimes you actually need to communicate with external applications. So instead of using start activity, you call a start external activity. But you can see like how this shifts the paradigm in which, like by default, you need to use the safe abstraction. But then if you want to do something unsafe, which is like call an external app, you have to use the start external activity. So this enables very development of tools around these abstractions. Basically, we developed lint rules, which basically say that hey, it's a bad method use. You don't want to use start activity. Use start activity from Secure Context Helper. Also, like if you use start external activity, then we know like, oh, we can throw up a warning message to show developers like, hey, you might want to consider like what are you doing, like the implications of what are you doing, like start external activity. And it also makes it easily analyzable, like the app easily analyzable. You know where exactly the outflows, the exfiltration can happen from your app. So it makes it easier to like for security people to like go and look at it, or for tools to go and look at it automatically. Another class of bugs that could happen in Android is like basically XSS holes. So you might not imagine like, because it's a native application, so we're all running Java code, XSS holes can happen. But many applications have at least one web view in them, essentially. So, and generally the code like this, vulnerabilities like this take this format. So you get the intent, and then you like basically get some data from the intent, and you usually shove it into the URL, and you load it into the web view inside the browser. So the attacker could basically supply an XSS vector like JavaScript, or he could supply file URLs, or like what makes it complicated to audit this code, these type of code paths is like you generally have JavaScript bridges, so you don't know what the extent of an XSL, or the impact of an XSS hole can have. So you can say like, maybe you could do some certain actions in the app, like which were not allowed before with using an XSS hole. So it's really dangerous to leave such code paths in here. So what we decided to do is like split the context. So this is, we split the context of web views. Like there's sensitive web views, which hold user cookies, like the pearls of like user data, essentially, like the user cookies. And there's non-sensitive web views, which we can load external URLs in. So in iOS, we load it inside the app. In Android, we load these external URLs. We delegate to the system browser. But when you actually load a URL in the sensitive web view, we actually pass it to the standardization function, which maintains like it's a central point in which we can maintain all the whitelisted list of URLs that are allowed to load. And these are usually like Facebook URLs. So we trust these URLs, and these load only over HTTPS, and we know that these are only URLs that are allowed to load inside this web view. So this way we can prevent these class of bugs essentially by using whitelisting instead of blacklisting. So another component inside Android is content providers. We find content providers really helpful in our applications, and I think others do as well. Like people use these all other places. So what content providers are like front ends for SQLite databases. So generally, like people implement it like this. Like what they do is they inherit from content provider, and then they implement this query method where they do this, use a SQLite query builder abstraction to build a SQL query, and then they execute the query in the database. So, so like content provider exact opposite of what we want in this safe by default framework, essentially. So they're like not protected unless, of course, you protect them by permission in the manifest. Great. So why is this bad? Is because like if you look at this code, like this looks like a prepared statement abstraction, but underneath the hood, SQLite query builder actually concatenates strings together and makes strings to do SQL queries. So this is a potential like SQL injection bug essentially in your application if you leave these content providers unprotected. And content providers are particularly important because they give you direct access to the database essentially. Like you can execute arbitrary queries with a SQL transaction, and people store like access tokens and stuff inside the database. So if you want to protect those data, those are pearls of user security essentially. So another class of bugs that we actually like really are concerned about is permission stealing. So even if you actually do protect your content provider with a permission, what happens is that like an app could come in before you and then actually declare your permission. Like permissions are nothing but strings in Android. So app just declares this string is mine. And then later when your app comes around, you don't own that string anymore. You don't own the permission anymore. So then basically like it can go and inspect your content providers directly. So permissions are not useful to protect content providers at all, like based on like what level of security we want. So what did we do? We engineered our own abstraction. Great. We engineered our own abstraction for this, which tries to prevent all these classes of bugs. And it's really simple to use. So it's called secure content provider. Instead of inheriting from content provider, if you want this security, you inherit from secure content provider. Not that you want this security, we'll enforce the security using tools. Essentially, we'll say, like, why are you using content provider? Don't use this. Use either a secure content provider or something else, which is the equivalent is public content provider. And instead of implementing query and insert, you implement do query and do insert. So developer, he just has to migrate to this framework, he just has to move code from one place to another. That's it. And it's like transparent wins essentially all over the place. And it gives security as well as like ease of use abstraction. So even if you forget to put the advantage of this is that even if you forget to put a permission in the manifest, secure content provider, what it does is underneath the hood, it checks the signature of the app that's actually requesting the transaction, the SQLite transaction, essentially to your the IPC transaction to your app. So you can protect it to only this white list of signatures are allowed to like access this. And in our case, only Facebook apps are allowed to access this content provider. Great. So another thing I want to talk about was logging. So logging is very useful for Android, like anyone, right? Like Android developer is debugging, and like you want to log. Sometimes you want to log like HTTP requests or something to log. So how logging works in Android is that there's a log device, which and there's an API in Java land to actually access the log device. So it's called log, aptly named. So what happens in older versions of Android, you can actually and there are a lot of them still in existence, you can actually inspect logs directly. Like you can use this tool called Logcat, and other applications can actually like inspect the logs given if they have the required permissions to do so. So then this puts a burden on the developer. It's like, oh, I have to log to like do my job, but I also have to remember to remove the logging once I ship the code to production. And this could result in bugs where like people leave logging statements inside the code when you release it into production. So we actually like designed this API called blog instead. It has the same interface as log, so just one extra character you have to type in. But it dynamically decides whether or not the app is in a production environment or a debug environment. In a debug environment, turn on all logging. In a production environment, turn off all logging. So without any code change, like based on dynamic environment, it basically turns off all logging. And hence, security wins. Another way like application components communicate with each other in Android is like through broadcasts. So again, like this case of start activity, like as I mentioned before, like if you misuse this API, you could result in like another application getting your whatever if you put private information in this. So what we did was we created this interface called FB Broadcast Manager for ourselves, which has a start send broadcast. So it basically has this bunch of types. Instead of like using broadcasts, if you want to send a broadcast cross-process, you use cross-process broadcast manager. If you want to send a broadcast inside your process, you use local broadcast manager. If you want to send a broadcast across apps based on a permission, you send permission-based broadcast managers. And you're not allowed to enable, so all of these like enforce at least 1 degree of security, is that like other applications cannot get your data, essentially. And it makes it hard to do the wrong thing. We're using lint rules, like it makes it hard to do the wrong thing. And it makes it really easy to do the right thing, which is like, you want to communicate across processes, why reinvent your own system? Use this API instead. So this covers like a lot of use cases, and like developers use this to send broadcasts all over the app, essentially. So let's talk about like network threats, essentially, the next type of threats that we want to deal with. So when we were looking at network threats, we use SSL to communicate between our application and our Facebook servers. It was all full SSL. So we were wondering like what causes man-in-the-middle vulnerabilities to happen. We don't want man-in-the-middle vulnerabilities in our application at all. So we tried to analyze like what could cause man-in-the-middle vulnerabilities to happen. So one reason could be like you use different SSL stacks in your code base. Like you use 5 different SSL stacks for various reasons, maybe. I don't know what your reasons are. But then, and like one of them has code like this. This looks like it does SSL validation correctly because it uses SSL sockets, right? So it must do SSL validation correctly. But it actually like forgets to do hostname verification, which like completely destroys guarantees you get by SSL. So like this is bad. Like so you want like one stack which does it correctly, right? But even if you do one stack which does it correctly, like there's product code could just go ahead and decide like, OK, we will like replace HTTPS with HTTP. Cool. Now whatever you did correct, or whatever SSL validation you did correctly is like nullified because all the requests are going via HTTP now. Great. So this is there's no technical solution to this problem unless you've enforced lint rules. But there's a core reason for this problem, like why developers would want to use HTTP rather than HTTPS. Basically, the root cause of this, like when people look at SSL, they think of SSL as like slow. Hey, this makes my product go slower. Like, why should I use this? It makes users' lives better, but like it makes the product experience worse. Like, why should I use this? So instead of like forcing SSL down people's throats, we try to focus on like how to make it faster and easier to use for developers. So like how to make it such that developers won't screw up by using incorrect use of SSL APIs, or how to make it such that developers won't feel that this is making their product go slower. So we engineered this abstraction called SSL Socket Factory Helper, essentially. So we spent a bit of time implemented this. So what SSL Socket Factory Helper does is like it provides you in iOS, we call it FB requester, which like encapsulates all the details of SSL inside it. So it basically abstracts away all platform differences from the developers. So they don't have to worry about how to get performance from SSL. So it does like it enables features like it works around bugs and enables features, platform bugs, and enables features like session tickets, which enable like resumption of SSL connections. So this makes SSL faster. If you have less round trips, then your SSL is faster. It also like enables SNI for like better certificate validation. Like it helps like reduce the number of SSL certificate validation bugs in our in production environments as well. It also like enables features like security features like certificate pinning and logging. So essentially, we want to log to make sure that, hey, we want to know whether somebody's man-in-the-middling us in the wild. So we do this at one place. If everybody's using this abstraction, then we know that, essentially. So what we found is like people naturally migrated to this abstraction. When we joined together the security and performance characteristics of SSL, like people naturally migrated all their code to this one abstraction. And we have like one SSL abstraction now in our code base. It's great. So we decided to take it a step further. Like we pushed Speedy inside our application to reduce the overhead of SSL completely. We found that like when we use Speedy, like because of the multiplexing of connections, it actually reused connections much more efficiently. And hence reduced, because if you have to make less SSL connections, SSL overhead is reduced. All of this along with session tickets, amazing wins, essentially. So like I think the lesson to be learned in this with analyzing this is that security people, instead of putting our blinds on and like focusing on only security, like maybe some ways of like actually influencing security is to improve the experience of the SSL frameworks itself, essentially. So I want to now talk about like how we store user data and mobile applications. So another aside, essentially. This is also very point that's very important to us. So in mobile applications, caching is mandatory. Like you have to cache data, otherwise like you're needlessly like costing users network bandwidth to go and request resources that they just requested, like for example images. And like networking, there's no like browser to do the caching for you, so you have to implement caching yourself, right? And so we also implement caching ourselves. We cache images, we cache like text, we cache other things. But for many users, we have to recognize that caching the storage spaces they have on their phones, like the typical Android user has very low storage on their phone. Like not enough to cache like the whole internet on, but like not like nobody has that, but it's still like pretty low. So we have this trade-off to make between like, do we improve their performance? Do we improve the network utilization by actually like fetching less data, or do we like, or we have to while being responsible with storage as well? Like, how do we do these two things? So what we realized is that there's this expandable storage on Android, which is the external partition. On some phones, it actually is a real SD card, essentially. So usually typical phones have like real SD cards on their external storage. So we thought that we could mitigate some of this storage cost that users face by moving some of the storage that we use in some of the data we store in internal storage to external storage. So then users can decide whether or not, like if they want better like network performance, then they'll like actually expand their SD card, essentially. Like they want to fetch less bytes over the wire, they'll expand their SD card. And they can get offline access to the app and stuff. But the way the Android privacy model works with SD cards is that SD cards are mounted as world-readable partitions. So this is a problem. Like before we were getting like isolation for free because Android uses Unix user ID isolation, essentially. But now we have to worry about like what happens when we put this data on the SD card. Can malicious applications muddle with it? Can malicious applications exfiltrate data out of the users' apps? So we have to worry about this. So we decided like to safeguard the privacy of users is like utmost concern to us. So we decided we want to encrypt the data on the SD card, essentially. So, but then when evaluating like the existing libraries on Android and like Bouncy Castle and some of the other Java APIs, we found that they were like slow. They were memory hogs, not designed for Android, like really slow. So we decided like let's manage memory ourselves. Let's create our own our encryption API for Android. So we created this library which we call it Conceal. Cool. So then basically what it does is it uses certain encryption libraries from OpenSSL to do encryption in native code. And then it manages memory efficiently between native code and Java code. So like memory efficiency is of the utmost important to us in this library. And it turns out like when we manage this memory more efficiently and we use OpenSSL underneath the hood, it is significantly faster than like the native provided libraries in Android. And the target for this is like typical Android users, typical Android phones, which have like low memory and slow processors, essentially. And we use like we use AES GCM encryption for this. So it's authenticated encryption. We use like state-of-the-art authenticated encryption techniques for this. So we think that other like developers like you guys, if you have mobile applications, you also struggle with this like trade-off. Like this trade-off between should I store data on the users, should I use more data on the user's device, or should I store it on an SD card, but then privacy implications of this. Like there's all these trade-offs that you have to make. So we've decided that we want to help you guys out with that, and we've actually we're decided to open source this library that we have. So we hope that you find use in this. So actually make this app keep the user's data safe inside the SD card. Like if you decide to store it somewhere in a public location. We also it's not a general purpose crypto library essentially, so it doesn't actually do everything that a crypto library does. It wraps OpenSSL and uses certain encryption APIs, and what it does quick fast essentially. So we open sourced it right now. You can go and check it out. It's open sourced. So it's out there. You can go start using it right now. So we're hoping that we're also hoping that we're really looking forward to the community support to actually develop this library further, to actually go and improve the performance and efficiency of this library, to get pull requests from all of you guys. If you're really interested in, if you're really passionate about security and setting new data standards for securing data on mobile devices, that would be really awesome. Yeah. Go ahead, check it out. That's all I have. Yeah.
Great talk. Thank you. My name is Yang.
Got a mic.
And thank you. A couple of questions. I haven't done Android development for a while, so maybe please bear with me. Regarding the content providers, just to make sure I understand, the library is supposed to be used inside the content providers to mitigate the risk. Am I correct?
So the way that our library works is that we actually the way you actually use a content provider usually is that you inherit from content provider, you extend the content provider. The way our library works is that extends from content provider, and then that implements the stub functionality, and that implements that as final methods. So query and insert and all that stuff is final methods, so that subclasses cannot override them. And then your subclass content providers inherit from secure content provider instead of inheriting from the system provided content provider.
Okay, so you are providing the protection at the content provider level.
Right. Exactly.
Okay, great.
Yeah.
The second question is that it's great that you are doing SSL, all of this yourself. And how much performance improvement did you get in your measurement?
So there's that's a very nuanced question that you're asking, how much performance improvement in the case of there's latency, there's client latency and stuff like that. So very basically how we prefer to measure performance improvement of SSL is that whether or not how much overhead SSL has on the TLS connection essentially.
Yeah.
So I don't recall the numbers exactly, but then we got a significant performance improvement by doing stuff like actually SSL resumption. So your latency is major cause of your SSL overhead.
Yep.
So because of the handshakes that you have to do and stuff like that, and then when we reduce latency, we reduce the SSL overhead significantly. There's also server-side aspects of SSL and other things, but then yeah.
Sure.
Yeah.
And did you implement Speedy yourself?
No, we actually use open source libraries to implement Speedy, which implement Speedy as well.
And last question regarding your key, your encryption. How do you manage the keys?
So the keys are actually stored in internal storage. So the keys are small data. So because we store if you store access tokens in internal storage, you're providing the same security for the key as your access token essentially. So we store the keys in internal storage. Okay. So which are protected, yeah. Which we assume to be protected. We're assuming non-rooted phone threat model essentially.
And are you making any trade-offs, right? So if it is all good, I would imagine that.
Well, it's essentially encryption does have some overhead. It doesn't come free. There's there's a little bit of memory overhead, and there's a little bit of performance overhead. But then it's in milliseconds essentially. It's you can't feel it essentially. We've used it. It feels really good.
Yeah. So I'm comparing it with the default encryption libraries.
Right.
So in order to, most of the time you have to make trade-off to gain something. But in this case, what is the trade-off?
So the default encryption libraries are a bouncy castle backed, in previous versions of Android. So they're not designed for Android in particular. So basically, they were not designed to be optimal memory usage for Android phones specifically. So the trade-off that we did was that we actually managed memory more efficiently. We used OpenSSL. So we made it such that we would perform better on Android phones. So there was no requirement for a trade-off in this case because the default libraries were not designed to be performant on this platform anyway.
Are you talking to Google to make to get?
So Google actually with KitKat Google has done something similar. It has changed the default backing to OpenSSL. So it will actually perform really well on your encryption on KitKat will perform really well. But then again, you can't use default cipher schemes and stuff. So we have an aside on the website. We talk about KitKat performance as well. You can go to check it out if you want to read it. Yeah.
Okay, great. Thanks.
Yeah. Awesome.
Do you have any encryption for SQLite? Do you store SQLite out?
No, right now we store SQLite in the internal database.
Do you have any planning of improving Conceal?
We're always looking at improving stuff, but then we don't have plans on anything at current essentially.
Okay.
Yeah.
For the your external storage project, what version of Android are you storing?
So it works from Froyo upwards, but like officially we're supporting like Gingerbread upwards or something else. But it works
Gingerbread, okay.
but it works for Froyo upwards essentially. Like practically it works for Froyo as well.
Mhm.
Yeah.
For your SSL implementation, do you need server-side support as well?
No, you don't need server-side support for this implementation. You can implement, like there's customizations you can do, which like if you want to store like persistent keys on the server and stuff like that, then maybe you can implement your own custom keychain, which will like store keys somewhere else or something. You can.
No, I'm talking about the SSL factory. So you are saying that supporting the session ticket.
So
SNI,
your server has to support like stuff like SNI and session tickets, which modern servers usually do support. Like those things are required to get the performance you need. But then SSL is designed in such a way that it'll back off. Like if your server doesn't support those features, like it'll just back off and then use the default whatever like the server supports. Essentially, it'll negotiate between client and server to support whatever.
So you are still vulnerable to some kind of active attack that disrupt your connections until you back up to the least.
So we don't back up to any HTTP connections.
No, I'm not talking about HTTP, but you could still back up to SSL version 3 or something like that, right? Because it's a native Android.
So we prevent against that in our applications. Like we enforce minimum TLS support, essentially. Like you want to have this much support, essentially. But there's some things we can't do, like some cipher suites that are not implemented in like some versions of Android, which unless, of course, we ship a custom completely open SSL build, which is really large if you look at it. Like, so unless we ship a completely custom open SSL build, we can't do anything about it. But then in old versions of Android, some cipher suites are not supported. So we have to like back off to like some cipher suites which are not the best we would prefer, but then like that's something.
Okay, thanks.
Yeah.
Any other questions?
Yep.
Do you think the security differences of backing off to an obsolete cipher suite, for instance, would be a big deal? And if they were, would you say you're installing this on a really old version of Android, your security guarantees aren't going to be as good as if you...
So we're always looking to, one is like we're always looking to improve the SSL performance. So we have plans to do interesting things with that. But then like we're always looking to improve stuff. So like right now, that is the situation. Like right now, the situation is that for all Android apps, essentially, you are susceptible to like the minimum cipher suite that the OpenSSL that ships with the Android system provides. But then there's always situations, room for improvement, and we're always looking to improve that stuff. Yeah.
Add a little more color to that. It's been a while since there was an Android device shipped that we had to completely cut off, but we do periodically go through that.
Yeah.
Older devices need to get cut off.
Yeah.
I believe the last one was at least.
So there's some devices that don't support SHA, like that don't SHA. So like we.
So you have certain lower bounds.
Yeah. Essentially, yes. That's exactly.
Yes. I forget the cute Android code name where we cut off the bottom at and blacklisted a few devices, but they're at least several years old at this point.
There's like some devices which can't SHA, like I told you. It's pretty